Let's go ahead and just jump right in. So in this video, we're going to dive into atrophy and metaplasia. So as you see right here, by the end of this video, what you should understand thoroughly is atrophy and metaplasia basics. We're going to go into some high yield insights, mechanisms like the ubiquitin proteasome degradation, cancer risks, clinical relevance, and also USMLE practice questions. These practice questions are essential not only to solidify your understanding, but also to test your knowledge on the subject. So I always really recommend to stay to the very end. Our videos are focused on high yield concepts specifically for USMLE Step 1, but really anyone interested in learning about disease processes will gain insight from these videos. So we're going to start here by talking about atrophy. So atrophy is shrinking under decreased stress. So the definition is a decrease in organ size due to reduced stress. So what is meant by reduced stress? There are several different mechanisms that apply. So hormonal stimulation, disuse, malnutrition, or excess nutrition as well. And also a reduced blood supply. One way that I like to think about atrophy is relating it to a plant that's no longer being watered. For example, its leaves, which you could say represent the cell size, begin to wither, and also some of the branches, which could represent the cell number, also start to wither away to conserve energy. Just like a plant tries to conserve its life, reducing its size and number, so does the human body. So when it comes to atrophy, though, it happens in two distinct mechanisms. The first is a decrease in cell number and a decrease in cell size. It's very important that you recognize that atrophy is both a decrease in cell number and a decrease in cell size. So the first one we're going to talk about is a decrease in cell number, okay? So a decrease in cell number is achieved through apoptosis. What is apoptosis? Basically programmed cell death. It's highly regulated, and basically cells self-destruct to maintain tissue health. Also very important to recognize in terms for USMLE is that apoptosis is a natural occurring phenomenon and does not include inflammation. So I cannot reiterate that enough. When apoptosis happens, there is no inflammation. So apoptosis or programmed cell death is like the cell's self-destruct system to normal. It keeps tissues healthy. And we're going to go through how it works here. So how apoptosis works. First, what happens is there's going to be a signal activation. So the cell gets a signal to start the process. This can come from inside the cell, like for example, if there's damage to DNA, or it can come from the outside. It gets a signal saying it's time to die. All right. Then once the cell receives a signal, key proteins are activated. What are the proteins? They're called capsaces. Basically, capsaces are turned on, and these act like scissors that break down important parts of the cells. So when I say breaking down the cell, what does that mean? It basically means the cell's DNA is cut into pieces. The cell shrinks. It's very important that you recognize that the cell shrinks because other mechanisms, the cell actually expands. So the cell shrinks, and its parts, like the mitochondria, are broken down into smaller pieces. Cells parts are broken down. What happens is it's removed. How is it removed? Basically, nearby immune cells like macrophages eat the dying cells and recycle its part. So this makes sure there's no mess left behind. So a metaphor, think of apoptosis as tree shedding its leaves in the fall, okay? The tree is the organ. So the tree stays healthy by discarding unnecessary or damaged parts, like the leaves or the cells, to conserve its resources for the next growth cycle, okay? So that's a decrease in cell number. Now, next, we're going to go through a decrease in cell size, all right? So this is mediated by two distinct processes, all right? So a decrease in cell size first is mediated by the ubiquitin proteasome degradation. I know this is a big word, but basically what's happening is the cytoskeleton proteins are tagged with ubiquitin. So ubiquitin tags the protein. It's like basically a marker that says, okay, destroy me signal. And once it has the signal, it's degraded by proteasomes, all right? Ubiquitin, tag me, proteasomes are the degradation. This is especially important in muscle atrophy, where contractile proteins are broken down during disuse. So an example of this could be prolonged bed rest or immobilization that will trigger the ubiquitin proteasome degradation. A metaphor, you could imagine pruning the branches of a plant that doesn't receive enough sunlight to ensure, remaining leaves survive. In fact, I like to use these metaphors because, sometimes these are hard concepts to understand. So the first way that a decrease in cell size happens is through the ubiquitin proteasome degradation, the TAGIT mechanism. The other way is through a process called autophagy. What is autophagy? Autophagy is cells form autophagic vacuoles that engulf damaged organelles and proteins, which are then broken down by lysosomal enzymes. Okay? This process recycles cellular components to maintain energy balance during periods of nutrient deprivation. So you can think of autophagy as a compositing process. The old withered leaves or damaged organelles are broken down and reduced as nutrients to support the plant's survival or the cell survival. Okay, so clinical relevance. Autophagy is activated in states of starvation and is also implicated in neurodegenerative diseases like Alzheimer's, where impaired recycling contributes to disease progression. All right. So another clinical relevance, like we just talked about, Alzheimer's disease, muscle atrophy, prolonged immobilization. For example, wearing a cast, they don't receive the signals needed to maintenance and growth. All right. So the breakdown process, how it works is proteins in the muscle cells are tagged via ubiquitin and broken down by proteasomes. Then the damaged or unused cells parts are recycled for energy with autophagy. The result, the muscle fibers shrink. Next, we're going to go ahead and dive into metaplasia. So we're going to go ahead and change topics here a little bit. So metaplasia is adapting to new stress, okay? So metaplasia is when one cell type changes to another to better handle new stress. So imagine one way you can think about metaplasia is, when it's cold outside, you're going to switch your sandals to boots. You're not going to wear your flip flops anymore. You're going to want to change to something that's better adapted to a rough terrain. So the new shoes could represent your new cells. Basically, they replace this adaptation, while protective in short term can have significant long-term consequences if the stress persists. So metaplasia, generally speaking, is reversible, but if it's long-term, if the stress persists, it can be very detrimental to the body and actually can lead to cancer. So moving forward, so the definition of metaplasia is replacement of one type of surface epithelium, so like squamous or columnar, with another that is better suited to handle the new environment. Remember, the epithelium surrounds the cavities of the body, like your blood vessels, your throat, your GI. The reprogramming of stem cells at the basal layer leads to the production of the new cell type. Importantly, this process is reversible, okay? Metaplasia is reversible if the stressor is removed. Now, clinical relevance, while initially protective, persistent metaplasia can progress to dysplasia meaning bad growth, like we talked about in the last video, and eventually can lead to malignancy or cancer. So classic examples of this are Barrett's esophagus, okay? Now, I'm just planting seeds right now. It's important not to get too lost as we'll continue to dive deeper into all of these diseases we're talking about. However, it's very important that you start to plant these seeds and begin to gain a better understanding for yourself. So in Barrett's esophagus, what happens is the normal esophageal lining, which is non-keratinized squamous epithelium, which is specialized for handling friction from the food but not acid. In Barrett's esophagus, though, what happens is acid reflux, chronic exposure to gastric acid, cause metaplasia. It switches its sandals to boots. So basically what happens is in Barrett's esophagus, the non-keratinized squamous epithelium is replaced with non-ciliated mucin-producing columnar cells. They're better suited for, protect against the acidic environment. If untreated, persistent reflux can lead to what? Dysphagia and dysplasia, and also progress to adenocarcinoma of the esophagus. Additional couple examples that are often brought up in USMLE: smoking induced bronchial metaplasia. So basically, normally bronchial epithelium are pseudostratified ciliated columnar cells, but with chronic smokers, chronic exposure to smoke leads to a change in to stratified squamous epithelium. This is because the body thinks it's better to withstand the irritation and constant stress. Persistent metaplasia can lead to squamous cell carcinoma in the lung if it doesn't resolve. Another commonly tested example is vitamin A deficiency. And vitamin A deficiency results in metaplasia to keratinize squamous epithelium, which is also called a keratomalacia, leading to dry, thickened conjunctiva and impaired vision. And lastly, one more example we're going to talk about right now while we're at it is myositis ossificans. Basically, what happens in myositis ossificans is connective tissue within the muscle undergoes metaplasia, growth to bone during healing after a significant injury. So this process is non-malignant, but can impair function and cause pain. Key concepts now. Let's get back to the key concepts. Number one, reversibility. Early removal of the stressor is imperative because you can reverse the metaplasia that can eventually lead to dysplasia or even cancer. You want to get rid of the stressor. So one, it's reversible. Two, progression to cancer, right? Metaplasia often precedes dysplasia and also malignancy, like we talked about, Barrett's esophagus to adenocarcinoma. There are exceptions. Certain types of metaplasia, like apocrine metaplasia of the breast, are not associated with an increase of cancer. Another example is intestinal metaplasia of the stomach due to chronic H. pylori infection, which increases the risk for adenocarcinoma, but not in all cases. These are commonly tested ideas. Additionally, osseous metaplasia, where bone forms in soft tissue, example in chronic inflammation or injury, is typically benign and does not lead to malignancy. Okay, so these are some key concepts to remember. We'll go ahead and move on. So pathologic and physiologic metaplasia. So metaplasia can be both normal and abnormal. Okay, so we're going to break this down. First, we're going to start with physiologic or normal examples. Okay, so normal examples of metaplasia. Cervical squamous metaplasia during puberty of the female, the cervix adapts to hormonal changes. All right, so the metaplasia, the cervix grows during puberty. Another common example is endometrial glandular proliferation during the menstrual cycle in response to estrogen, which is reversible and physiologic adaptation. It's a normal process in females. Another really common example, it's not as high yield, but still good to be aware about, is metaplasia in the respiratory epithelium of individuals living in a high altitude region. This is where epithelial cells adapt to reduce oxygen levels by increasing alveolar surface area through structural modifications. Lastly, we'll talk about lactational changes in breast tissue. So ductal epithelium undergoes hyperplasia and secretory changes in response to hormonal stimulation during breastfeeding. These are normal. Okay, so these are physiologic, non-cancerous. These are normal processes in the body. Pathologic examples, time and time again, are very high yield. We've talked about a few of these, which goes to show why we are planting seeds, but we will continue to dive into all of these as well. The main idea is you just get a brief understanding, okay? So vitamin A deficiency. Vitamin A is essential for differentiation and specialized epithelium. For example, the conjunctiva of the eye. Deficiency results in metaplasia of the conjunctiva to keratinized squamous epithelium, also known as a keratomalacia, leading to impaired vision. Myositis ossificans, like we've talked about, is an inflammation or trauma causes muscle tissue to transform into bone. So metaplasia of the mesenchymal tissue. All right. Third, chronic gastritis. Persistent H. pylori infection causes gastritic epithelium to undergo intestinal metaplasia, increasing the risk of gastric adenocarcinoma. Okay. Squamous metaplasia in the bladder. Chronic irritation, such as with long-term catheter use or infection, can increase the risk for replacement of transitional epithelium with squamous epithelium. This carries a risk of squamous cell carcinoma. Pancreatic acinar to ductal metaplasia. So chronic pancreatitis triggers transformation of acinar cells into ductal-like cells, which is a precursor to pancreatic cancer. And lastly, bronchial squamous metaplasia. Chronic smoking causes pseudostratified ciliated columnar epithelium in the bronchi to transform into stratified squamous epithelium. This increases the risk of squamous cell carcinoma of the lung. Now, Clinical correlations and exceptions. Metaplasia can often be reversed if the underlying stressor is removed. Early intervention plays a critical role in preventing progression to dysplasia or malignancy, aka cancer. So, like I said before, one example is Barrett's esophagus. Treating acid reflux can reverse metaplastic changes in the esophagus. Bronchial metaplasia, stop smoking. If you help your patients stop smoking, this can reverse metaplasia caused by chronic exposure to cigarette smoke. Additionally, salivary glands, chronic inflammation, such as in Sjögren's syndrome, can induce metaplasia, where glandular tissue becomes duct-like. Managing inflammation may help prevent further progression. Additionally, cancer risk. Persistent metaplasia often progresses to dysplasia and eventually malignancy. You'll notice that there's redundancy in these videos, and it's for a reason. You need to understand these concepts. These are very high yield. Again, a couple examples: Barrett's esophagus, intestinal metaplasia of the stomach. This is associated with adenocarcinoma, though not all cases progress to cancer. Gallbladder metaplasia. Chronic colitis or gallstones can induce epithelial metaplasia, potentially progressing to dysplasia and gallbladder carcinoma. Endocervical glandular metaplasia, so chronic infections such as chlamydia, can lead to glandular metaplasia, which predisposes to cervical dysplasia and malignancy. A couple exceptions that are also very commonly high yield. Metaplasia of the breast carries no risk of malignancy, and also osseous metaplasia. Bone formation in soft tissue due to chronic inflammation is typically benign and does not lead to malignancy. Okay, good job. I know that was a lot. It was kind of a heavier section. Let's go ahead and dive into our USMLE practice questions. Like I will always tell you in the beginning, start with the end. So, which of the following best describe these changes? Then read your answers. Then read the whole question. All right. So go ahead. I'll give you a few minutes and we'll come back and review. All right. So a 58-year-old male with chronic GERD presents for an upper endoscopy, which shows metaplastic changes in the lower esophagus. Which of the following best describe these changes? Okay. Answer A, replacement of squamous epithelium with columnar epithelium. Why is it not B? This occurs in the reverse scenario, such as chronic irritation in the cervix. Okay. Why not C? C, apoptosis reduces cell numbers but does not explain metaplasia. Okay. Why not D? Dysplasia often occurs after metaplasia and represents a higher grade lesion. Okay. Question number 2. I'll give you a few minutes. Okay, good job. Vitamin A deficiency was the correct answer. So why not A? So vitamin D deficiency affects bone metabolism, not epithelial differentiation. Why not C? Chronic conjunctivitis causes inflammation but not keratinization. Okay. Why not D? Apoptosis reduces cell numbers but does not lead to keratinization. Now, you'll notice that a lot of these questions are pretty difficult, and that's on purpose. It's to familiarize yourself. The more you continue to watch these videos and continue to practice, the easier these will become, okay? So don't get too discouraged. All right, lastly, I'll give you a few minutes on question number 3, and then we'll get back. Okay, correct answer was C, myositis ossificans. So why was it not A, apoptosis? Apoptosis does not explain the formation of bone-like tissue, okay? Why not B? Atrophy refers to the decrease in size, not abnormal growth, all right? Why not D? Dysplasia refers to abnormal cellular organization, not bone formation. So that concludes our section. Thank you for watching. If you found this video helpful, don't forget to visit thehealingpowerofnature.com for top-tier study materials, including our complete pathology book designed to make passing the USMLE 1 easy breezy. Your support means everything to us. Head over to our Patreon to help us keep these videos coming and also unlock exclusive study content like bonus materials, practice questions, and more. Together, we can make your journey to becoming a doctor smoother and more successful. Don't forget to like, subscribe, and share this video with your fellow future doctors. Until next time, happy studying, and remember, the power to succeed is already within you. Thank you.